designing a galvanic cell from a single displacement redox reaction. And remember, galvanic is the same thing as a voltaic cell. Those are both when the reaction is spontaneous from the redox coupling. Okay, so in order to work out what is going on here, we really need to understand two things. So the first thing is we need to be able to work out which process is a reduction process and which process is an oxidation process and write half reactions for that. The second thing we have to understand is that electrons will flow from the negative electrode to the positive electrode spontaneously. Okay, and that is exactly what is happening in a galvanic or a voltaic cell. We're looking at spontaneous flow of electrons, not flow of electrons being driven by an external current. That would be electrolysis. Okay, so we're going to flow from negative to positive. Opposites attract, right? Electrons are negatively charged, they're going to go to the positive end. The other thing you're going to need to know is how to label your electrodes, anode and cathode. Anode, the clue's in the name, right? Anions are negative, right? So anode, we're associating with a negative charge, okay? And the cathode, again, associate with that with cations, right? The cathode should be positive. There's a handy little way to remember this, and that is thinking about a red cat, whatever flavor of red cat you like an angry ginger kitty or like House Lannister from Game of Thrones. That would be a good one. Or if you prefer, like Harry Potter, right? Gryffindor is red and it's lions. That's kind of an angry kitty, right? So remember red cat because red cat will tell you that reduction is at the cathode. Okay, if you know all these things, then you should be able to label one of these voltaic or galvanic cells correctly. All right, so bearing this in mind, let's look at our actual redox reaction. We have nickel. So that's going to be an oxidation state of 0. And then we have palladium sulfate. We should know by now that the sulfate ion is SO4 2 minus, so that's going to make it palladium plus 2. I'm not going to worry about going ahead and assigning oxidation states to everything in the sulfate anion because I can see over here we have nickel 2 sulfate. So that means that sulfate must be our spectator ion. And then we have solid palladium. So we can see from looking at the oxidation state that nickel is being oxidized from nickel metal to nickel 2 plus. And we can see that palladium is being reduced from the plus 2 oxidation state to palladium metal. And this fits in with what we know about the activity series of metals, right? That nickel is above palladium in the activity series, so nickel metal can displace palladium from a solution of its ions. Okay, so let's write our half reactions then in terms of oxidation reduction. So my oxidation half reaction is that nickel solid is being oxidized to nickel 2 plus, AQ. And to balance this, I am going to need to add 2 electrons, right, to balance the charge. Okay, and then my reduction half reaction will be that palladium 2 plus, if I can find my 2 plus, is being reduced to palladium metal. So I will need to add 2 electrons to the left side of this to balance the charge. Okay, so we have a reduction and an oxidation half reaction. We know reduction occurs at the cathode. That is our positive electrode. So the electrons should be flowing to the cathode, and our oxidation half reaction is the one that's going to be happening at the anode. So that is where the electrons are leaving from. And that makes sense because look, the electrons are on the product side of the oxidation half reaction that's occurring at the anode, and they're going through the circuit to combine with the palladium 2 plus at the cathode end and yielding solid platinum metal, which is going to be building up on the electrode, which is electrode 2 in this case. So the balance half equation that happens at the cathode of this cell will of course be the reduction half reaction. I think I'm going to just have to take both of these and then delete to get them in the right box, although we've already said which one's which. So there's my reduction half reaction, and then my oxidation half reaction is happening at the anode. Okay, so of what substance is electrode 1 made? So electrode 1 must be my nickel half cell, right? Because that is the one at the anode where the oxidation is occurring. So the way these electrodes are composed is going to be a strip of the solid metal in a solution of its ions. So it'll be nickel solid is electrode 1. Electrode 2 will be my palladium metal. The chemical species in solution S1, well, the solution is going to be my nickel sulfate, but of course, these are soluble ionic salts. So nickel sulfate AQ doesn't actually exist in solution. It will be nickel 2 plus AQ and the sulfate ion SO4 2 minus AQ. So do be aware of that for these type of questions, right? That we're dealing with soluble ionic salts, so we do need to break them apart into ions. And of course, the sulfate is actually a spectator ion in this case. It's not taking part in the equation. And then solution S2 on the cathode side is palladium in a solution of its palladium 2 ions. So that is the PdSO4. And again, PdSO4 is going to completely break apart into palladium 2 cations and sulfate anions. All right, so hopefully that is helpful for you guys. You just got to make sure that you can work out which is your oxidation reduction half reaction. Understand that electrons will always flow from negative to positive electrodes in a spontaneous reaction, and that oxidation occurs at the anode. So that is the electrode that is going to be negatively charged because electrons are coming off at the anode, and then those electrons are going to be attracted to the positively charged cathode. So that is where the electrons are going to, and that is the electrons being transferred in the reaction. Of course, that bit at the bottom in between those two beakers is a salt bridge, and that is necessary to collect the circuit, to connect the circuit.